For our last example today, we're going to do another digital design from the truth table, but we're going to select one where it's clearly the case that there are more rows that contain 1 than contain 0. And so in this case, it's pretty apparent that if we were to solve this problem using the same technique that we used in the previous video, there would be 6 terms, 6 product terms. We'd have, each one of them would have 3 inputs. There'd be a 6-input OR gate. That is not a good solution. So we're going to focus on the zeros. And what that means is that we're going to be deriving not f, but f bar. And so at the end, we're going to need to use DeMorgan's theorem to make our solution in the correct form. So here you can see that this would correspond to A and B and not C. And this one would correspond to A and B and C. So I can write my expression for f bar is equal to A and B and not C, or A and B and C. So I've written my expression. That's everything that I needed from the truth table. But it did, in this case, it said go ahead and simplify it. There's no part B where we redo it. I just want to do it one time. So let's factor A and B out of these terms. I end up with C bar or C. That just becomes 1. And A and B and 1 is just the same thing as A and B. So I can say that F bar is equal to A and B. One thing I like to do after I've done some Boolean algebra is to go back and look at the truth table and I say, wait a minute, would it have been reasonable to have just identified that this was A and any row that had A and B? And the answer is yeah, I guess if I would have been insightful enough, I could have spotted that, but I needed the Boolean algebra to help make it happen. So what I'm going to do now is I'm going to invert both sides of this equation. And that picks up a second bar on the left-hand side. So F bar bar, that's just the same thing as F. And then on the right-hand side, I have here A NAND B, which certainly we could implement, but I'm going to go ahead and use DeMorgan's theorem and say this will be A bar or B bar. When we're drawing these circuits, we tend to like to restrict ourselves just to AND gates, OR gates, and inverters, and preferably in 2-level logic if possible. Well, this is now in a form that is 2-level logic. This is SOP. Although there really aren't products, there is a sum, and it's sum of, I guess you could say it's a sum of products of just individual variables. So I'm going to have an OR gate here, and that will be coming from an inverter with A. Here's, here's the other input. That'll be coming from an inverter, which has B, and that's F. So this is the solution, and we could have obtained that solution in other ways. We could have done it if we would have done all the work to go through the Boolean algebra for this. We would have ended up with the same solution. Bear in mind that if we were to have used this solution, we could have just had A, B, AND gate, bubble, and there we go. So there's A, B, and F. It could be implemented with a NAND gate as well. And since I didn't specify that it had to be an SOP form, either of those solutions would be fine.